Well, good day to you wherever you are. The purpose of this is to, make lesson 3.5 available to those of you who are traveling or representing the school in different ways. So as a first part of the 3.5 lesson, I wanted to point out something that could have been presented better to you last time, and that is lesson 3.4, number 151, which you see in front of you. I'm just going to check something here. Okay. Testing. Yep, we got volume going good. All right. So anyway, on lesson 3.4, we talked about number 151, and we got to the same answer, but I want to show you a correct way to do this. So the function was for us to take a look at this. This is the function, and what we were supposed to do is determine the derivative. But before we do, we really need to know this principle, which has nothing to do with derivatives, and that is that when you take the log of a different base times t, and this is just an algebra thing, that's equal to the natural log of the thing you were taking the log of, t, divided by the natural log of whatever the base was. So this is just a principle of algebra of logarithms. The log base 4 of something is equal to the natural log of that something divided by the natural log of 4. As a result, that allowed us, once we know that, and by the way, the natural log of 4 is a number, it's a constant. And so it too can be pulled out of the problem. As you can see, I rewrote the function. 10 is a constant, and so is the natural log of 4. That leaves us with the other part of the problem, which is the natural log of t over the natural log of 4, over the natural log of t. So now that we know that, now we can go ahead and differentiate, and now it's rather straightforward with this constant out in front and ignored. Now you can take and do the quotient rule. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And then over denominator squared. T times 1 over t is 1. And basically, your derivative is done. So this could be just reiterated as the derivative. So anyway, I think the way I showed it to you yesterday, I showed this natural log of 4 being written in the bottom as part of the derivative, and it's not. It's actually part of a principle of logarithms. And I should have pulled that out first. We got the right answer, but this would have been a better presentation to you. Okay, let's get to the new work. The new work is called Implicit Differentiation. Implied is what that implicit stands for, as opposed to explicit, where it's really clear. And again, there's a nice presentation of this on the alternate website. You go there, you will see that they talk about, we're going to talk about functions like this today, where you have things like x cubed plus y cubed equals 6xy that cannot be solved for y. And because they can't be solved for y, you would think we can't differentiate, because every differentiation problem we've done previously, you solve for y and then you differentiate. Well, we're going to find that today this type of unit can be differentiated. This type of equation can be. Okay, so, all right, I don't know why that thing is in the way. Let's get that down here. All right, implicit and explicit functions. So like I said, they didn't give the best example. In the first example of an implicit function, they wrote this one, xy equals 1. Now it's implicit in that it's not solved for y, but this one can be solved for y, and it could be written as y equals 1 over x, like they did right here. The problem is some equations can't even be converted to explicit form. And so, like this one down here, how can we do that? And so, well, I'm going to just cold cock go right in and show you how you can do that. Just a second. Come in. I'm making a video right now.
I just wanted to let you know that the reason why I have a phone call is I just switched into the subject and I have it speaking, so I've been crashing at like weird hours. So that's why this isn't 7 minutes, but I've been on it for 2 weeks, so it's just like doing it. But I've been picking up on this.
You're doing better.
Thank you.
So, just had somebody step into my office. So I'm doing this from my office today. After class, I tried recording during class and something didn't go right. So I'm doing this after class. So we're going to take this function here on the bottom, and we're going to differentiate it. Okay, now let's see. I got to get a pen, something to write this down, because I can't do the copying at the moment. My free prescription expired. Okay, so now let's go off to the side. And let's take our first look at a problem like this. So we have x squared minus 2y cubed plus 4y equals 2. So that can't be solved for y. By the way, if you tried, you could get the x squared on the right side, and then you could factor a y out of the left. But the problem is there's another y in the parentheses, and when you divide both sides by the parentheses, you can't do it. You just can't do it algebraically. But that's okay. You can still differentiate, and that's what this lesson is about. So what you could do is just, let's take the derivative of the whole equation. So we put the whole thing in braces and we say, let's differentiate. And when you differentiate, I know, what do you do with an equal? Okay, you leave the equal sign be, but you'll see, all of that's pretty straightforward. The derivative of x squared, we already know what that is. That's 2x. What do you do when you get to a y term like negative 2y cubed? Well, treat it like a regular variable. So that would be what? Negative 6y, lower the power by 1. But because y is, over here, we're differentiating with respect to x. Because this is a non-x, you have to do the chain rule. So what we're saying is, go ahead, do the derivative, and then when you come to a non-x, you have to apply the chain rule. So I have to take it times the derivative of whatever y is. Next one is plus 4. But again, because it's a y term, we got to do the chain rule, dy dx. And when you differentiate a constant, that's 0. So you just kind of do it right over the equal sign. All right, so what good did that do us? Well, what we really want to know is, what is that dy dx? So the next step would be to isolate the dy dx. In other words, let's get rid of anything that's non-dy dx. For example, this 2x. And I will subtract that from both sides of the equation. All right, so we've got that subtracted. Now, we want to get dy dx by itself, and we can use factoring to do that. So dy dx factored out of negative 6y squared plus 4 equals negative 2x. And now we can solve for dy dx. And that is negative 2x divided by negative 6y squared plus 4. Now, so this is the end of our derivative down here. So what's unusual is we now have a y in our derivative, but that's okay. If they might, later on, they might give you a point to find, you know how before when we found f prime of x, whatever it was, then we could find f prime at whatever value of x they asked you by substituting 3 in for x. Well, when you get a problem of this type, you've got your dy dx, and then what they might say to you is, what's dy dx at the point 2 comma 9? Notice they're giving you more than just a single value because you need both x and y when you substitute in. We'll get to a problem like that in just a bit. All right. So there's just some more of the same thing here. Yeah. So why, right in the center, when you look at the part B of example 1 here, you see that they're trying to teach that when you're differentiating with respect to x, then when you're doing a non-x, like a y, besides the regular derivative of 3y squared, you're also going to have to, you're also going to have to do the chain rule and do the dy dx. So this is kind of a repetition from what I just showed you. All right. So let's take a look at a problem. So here's number 1 from the problem set from the assignment. You can see the problems up here in the top right corner. And the directions are find dy dx by implicit differentiation. Number 1 is x squared plus y squared equals 9. You may recognize that in algebra, that's the equation of a circle whose center is at the origin and whose radius is 3. Anyway, whether you recognize it or not, we're supposed to differentiate input. By the way, could we solve this for y? Could we make this explicit? On this one, we could. We could get y equals plus or minus the square root of 9 minus x squared. But despite that, they want you to do it implicitly as you look in the directions. So here we go. dy dx, put the whole thing in brackets. The derivative of x squared is, of course, 2x. The derivative of y squared is 2y, and because it's a non-x variable, I have to use the chain rule and multiply by the derivatives by dy dx. And then on the right side, the derivative of 9 is 0. Then it's just a matter of getting rid of the non-dy dx term, 2x, so I subtracted that in this step from both sides, and then just get rid of get dy dx alone by dividing both sides by 2y. And simplifying, here's your final derivative right here, negative x over y. Now, for example, what if I said find dy dx at the point 0, 3? So that means take your derivative, negative x over y, substitute in 0 for x and 3 for y, and you can see that the slope of that is 0. By the way, remember this circle? Center 0, 0, radius 3. So you've got points like 0, 3 up on the top, 3, 0 to the right, 0, 3 below, negative 3, comma 0 to the left, And I just gave you the point on the top, 0, 3. What's the slope of the tangent line? It would be horizontal. Oh, yeah, 0. That makes sense. Here's another point on the graph. What's dy dx at the point 1 square root of 8? And you could, okay, x is 1. They get negative 1 over the square root of 8, and you've got the slope, and it should be negative, because to the right, your tangent line would be pointing downhill from left to right. Yeah, maybe I could just quickly show you if we go to Desmos. If we go to Desmos, x squared plus y squared equals 9. We'll put that up. We'll put that in here. So there's our graph, and what we did is we found the slope of the tangent line at 0, 3, and sure enough, it's horizontal, so it's 0. Okay. If we had done 3, 0, we'd have had what? A vertical line which has no slope, so an undefined slope for that one. What was the other one I gave you? 1 comma the square root of 8. So that would be right about here. And you can see that one has a slightly negative slope. So this makes sense. I hope it makes sense to you. Okay, so that's number 1. Let's take a look at number 8. So on number 8, this one's more of an algebra challenge, but number 8 says the square root of xy equals x squared y plus 1. So there it is in brackets. We want to take dy dx of that. All right, so first of all, the square root of xy, as we normally do, we'll rewrite that using exponential notation. So, you know, that's this part right here. But otherwise, I didn't do anything. All right, now it's time to do it. What's the derivative of xy to the 1/2? Outside, you would do the power rule. Bring the 1/2 down, leave the xy, lower the power by 1. And then inside, we got a product rule, x times y. So the first times the derivative of the second, plus the second times the derivative of the first, which is actually times 1. Yeah, you don't have to write down a times 1. Okay. That's the left side of the equal sign. Now the right side, we have another product rule, x squared times y. The first times the derivative of the second plus the second, y times the derivative of the first, 2x. Why don't I need to do dy dx? Because this was not a derivative. It's the second times the derivative of the first. Okay, then it's just a matter of simplifying algebra and I mean, there's no more derivative. We basically have just executed the derivative, okay? And there's all kinds of horsing around you can do getting this thing equal. After you simplify this a little bit, you will notice that you wind up with, let's look at this line right here. When you look at this section right here, you will see that I've got dy dx 2 times. I've got it over here on the left. It's multiplied by this quantity. And dy dx is multiplied by this x squared here. So what I did is I got the dy dx terms on the same side. So first of all, I multiply, what's dy dx times these parentheses? Dy dx times x over 2 square roots of xy plus dy dx times y over 2 times the square root of x times y times the square root of xy. Okay? Actually, I'm trying. Well, I didn't do that yet. hang on a minute. What did I do? I've got to get my mind straight here. Yeah. Well, anyway, I don't know if I'm going to go any further, but the point is you get your dy dx terms together, and then what you do is at the very end, you got your dy dx terms, you factor out the dy dx, and then and when you factor that out, then you can divide both sides by the thing in the brackets. And that's pretty typical. Let's go on to number 14. Okay, here we have a trig problem. Derivative of the cotangent, the equation is the cotangent of y equals x minus y in brackets here. What's dy dx of that? So the derivative of the cotangent is negative the cosecant squared. That's a trig identity. We did it that day. We used the quotient rule. I think what we did is took cosine over sine, which is another name of cotangent, and then we did the quotient rule. And we came up with a simplified answer of negative cosecant squared. All right, but then because it's a y guy, I got to do the chain rule, dy dx. Right side, derivative of x, 1. Derivative of y, 1. But because it's a y, chain rule, dy dx. All right, now get your dy dx terms on one side. So I moved the dy dx terms to the right. So I added dy dx cosecant squared to both sides. And I subtracted 1 to get rid of this constant right here. This one right here. I want it, never mind. I'm trying to point and not mark it up, but I guess I can't do that. So this guy right here, I wanted to get rid of that, so I subtract. So anyway, here we are. So now I've got two dy dx terms on the right. I factor out a dy dx. Watch out for this negative sign. That's where that came from. All right. Now divide both sides by -1 plus cosecant squared. And, you know, -1 plus cosecant squared is a trig identity. That's the same as the cotangent squared. And the reciprocal of the cotangent squared is the tangent squared. So, you know, really either one of these would have been fine for the derivative. Okay, so that was 14. Let's take a look at number 26. Number 26 is y cubed minus x squared equals 4. Find the derivative at the point 2, 2. You know, if you do a really quick check, does 2 really work in that equation? 2 for each. That would be 2 cubed, 8 minus 2 squared, 4. 8 minus 4 is 4. Yep, that 2 is a point. So anyway, dy dx, the whole thing. Derivative of y cubed is 3y squared, but because it's a y, I also have to do the chain rule, dy dx. Derivative of negative x squared is -2x. Derivative of 4, 0. Get rid of the non-dy dx term. This one right here, add it to both sides. And then, you want to get rid of the 3y squared, divide both sides by 3y squared. So here is our derivative. Now, what's the derivative? And notice the notation I use here. What's the derivative at 2, 2? And now you just substitute in 2 for x, 2 for y. And simplify it. There it is. There's the slope of that line at 2, 2. Let's take a look at number 27. Y squared equals x squared minus 49 over x squared plus 49. And I want you to check out that one at the point 7, comma 0. All right. So, derivative, the whole thing. Derivative of y squared is 2y, but because it's a y term, I have to do the chain rule, dy dx. Equals, and then I've got what? A big happy quotient rule here. Denominator times derivative of numerator minus numerator times derivative of denominator, all over denominator squared. Multiplying things out and simplifying brings me down to this point. And then if you want to solve for dy dx, so you divide both sides by 2y, and there is your general derivative. Now, the answer to the question is, what's dy dx at the point 7, 0? Plug in 7 for x, gives you 1372 on the top. And when you plug in a 0 for y, that makes the whole denominator 0. So that's undefined. So let me show you what that looks like in decimals. So we've got y squared equals x squared minus 49 over x squared plus 49. Just had to quick write that down on paper. All right, so we're going to not see that. All right, so here we have y squared equals parentheses x squared minus 49 divided by x squared plus 49. And you see we have basically two what looks like parabolic regions. And we were supposed to find the slope at 7, the slope of the tangent line at the point 7, 0. And sure enough, at the point 7, 0, can you see it would be a vertical tangent line, and therefore has an undefined slope. So what we did here is appears to be spot on, correct. Okay, let's look at one more. Number 31. Yeah, we'll look at one more. Number 31, as you can see, is the function 3e to the xy minus x equals 0. And we're supposed to do this at the point 3, 0. So, derivative. 3 is a constant, so we don't need to touch that on the derivative. E to the xy, how do we take the derivative of that? Itself, e to the xy. And the problem is xy is an inner function, so I got to do the chain rule here, and the chain rule means I have to do a product rule, x times y. So that's what's going on in parentheses here. The first, x, times the derivative of the second, dy dx, plus the second, y, times the derivative of the first. The derivative of x is 1, so I didn't write it down. The derivative of this next term is -1, and the derivative of 0 is 0. Okay. Then I got to take this 3e to the xy times these two quantities in parentheses, the distributive property, which I did, that's what this is, 3e to the xy times x, dy dx, and 3e to the xy times y. And then, all right, so now the idea is get the dy dx term by itself. So I subtracted the 3y e to the xy. I'm sorry, yeah, I subtracted that, and that brought it over here. And then all I had to do is divide both sides by 3x e to the xy. Okay, there is our general derivative. I can't cancel those 3's because the one on top is being subtracted. So it's time to substitute. What's dy dx at 3, 0? And if you plug things in, so if y is 0, that's going to make this whole exponent 0, and e to the 0 is 1. Y is 0, so what you have on top here is negative 3 times 1, negative 3 times 0 times 1, which is 0. So 1 minus 0 is 1 on the top, and on the bottom, 3 times 3 times e to the 0, which is 1. So 3 times 3 times 1 is 9. There we go. The exact derivative at the point 30 is 1/9. All right. So hopefully that's enough. And it's pretty much what the kids got in class. That's enough for these students that were not in class. I hope you're having a good trip. Let's just take a look at the assignment here. For lesson 3.5, there are 2 odd sections, 1 through 19 odd, 23 through 33 odd. So that's the assignment. If you have some questions, you of course can contact me by email. And thank you very much for watching this video.